Yeah, hello. Well, in this little video about linear measurement, we're going to look at the basics of linear measurement and just run through choosing the most appropriate gear for the job and what the jobs might be and what have you. So we want to look at what is the best fit for the job. Now, a couple of things that come up in the course of this, of course, is range. That's how far something can measure. And the accuracy. How accurate is it? How close to the measurement is to the real value. Sometimes we never know what the real value is, but we do need to get an idea of what the manufacturers sort of have designed the particular instrument we're using for, and to what accuracy they're hoping to achieve. So let's say, for instance, we're using an EDM, electronic distance measurer or measurement or meter, whatever your fancy is, and the manufacturers might say, well, the accuracy, it has an accuracy of, for a measurement, an individual measurement of plus or minus 2 millimeters, plus 1 part per million. Well, what's this 1 part per million? Or ppm? Well, as I've said, it means 1 parts per million. So 1 part per million would be a millimeter per 1 million millimeters. A million millimeters is 1,000 meters, or 1 kilometer. So that's 1 millimeter per kilometer. So the accuracy over a kilometer would be 2 millimeters plus 1 millimeter, or round about 3 millimeters for a single measurement. If we do 2 measurements, of course, that would accumulate, and so it goes. So here's a bit of a question around this for you. A manufacturer states that their EDM, electronic distance measurer, measures to an accuracy of 2 millimeters plus 2 parts per million. How accurately could the EDM measure a line 567.46 meters long? Well, to work this out, we just try and keep things in meters. I think it's the best way to go. So we put out 2 millimeters, which is plus or minus 0.002, and we add to that 2, the 2 parts per million, times the distance, 567.46, divided by a million. And we put that into the calculator and we get this extremely large number. Plus or minus. We tend to work in absolute terms, so we just keep that plus or minus at the front there. Not worrying about signs too much, but tend to work in absolute terms. So we'd get 0.00313,492. Well, we did on my calculator anyway. And just rounding that up to millimeters, it's plus or minus 3 millimeters. Or as we say out on the job, 3 mils, plus or minus 3 mils. Now, you should note here that conditions apply. Environmental conditions, that is. So, depending on your temperature, pressure, and that sort of thing, the accuracy can change quite dramatically. So it's a qualified sort of thing that we're saying here. So just bear that in mind. Alright, well, now we've got a bit of a handle on what we're talking about here with linear measurement and accuracies and EDM and what have you. What I wanted to do is I put up this little table here, which first of all, from top to bottom, shows the linear measurement. This is distance measurement tools that most surveyors have available to them, although this is not an exclusive list, in order of sort of increasing accuracy as we go from top to bottom. And then across the top here I put a number of various typical scenarios that we might use our linear measurement gear for. The topographical survey, cadastral title survey, building set out, and control survey. And again, I've tried to put them in order of increasing accuracy, although there may be some sort of slightly blurred boundaries and what have you there. So let's have a look at our typical fiberglass tape, where we can generally measure plus or minus 10 mils with these, depending on how we tension them, getting them horizontal, provided we haven't pulled them too tight or hard in the past and stretched them, or a little bit missing off the beginning, and various things that happen to these tapes because they get into some pretty tricky situations. But generally plus or minus 10 mils is achievable with some care. Now the range of the tapes varies. This is the fiber or fiberglass tapes. The range varies from 20, 30, 50 and 100 meters there, not millimeters. Bit of a fox par there, but yeah, it's 100 meters. I meant to put there, but never mind. Well, I'm sure you can. All big boys, we can deal with that. So you can, however, measure in bays. You could measure 5 20-meter bays to get 100 meters, but obviously that'd be 10 mils per measurement. So these are not the most accurate tape in the drawer, so to speak, but they do have their uses and be pretty fine for a topographical survey. In a cadastral title survey, you might use your tape for checks and a rough set out if you were just wanted to position some pegs approximately in the right location before you put them in, or you're sort of marking something out for a client, and just to give them a rough idea of where things are going to go. And again, a similar usage in the building set out. Control survey, again, used for checks for gross error, and possibly little topo shots for location diagrams and what have you. So yeah, the old fibre tape, it has its place, but we must be careful that we don't exaggerate its accuracy. It's not the most accurate. Stadia, this is Stadia's sort of a thing from days gone by. For those of you that don't know too much about it, when you look through the theodolite, you can see the central cross here, and then there's a top and bottom cross here. If you're to read a levelling staff with the theodolite, the distance that you read on the staff between the top and bottom here, multiplied by 100, will give you the slope distance. So typically these have a range of up to 200. Typically they're used up to 200 meters, but they can be stretched out to 300 meters. But that means you would have to see sort of 3 meters of the staff, and sometimes it's not always possible, although you are using a 5-meter staff, and it sort of can be quite difficult to actually read the numbers accurately at that distance. Typically what we used to do was set the bottom cross here on the even meter mark, and then we could read the distance directly off the top. So if it was on, he set the bottom mark on 1 meter and read the top at 2.47, that would be 147 meter slope distance, and we could estimate down to 0.1, 0.2 of a meter. We would then typically either turn the central cross here up to the actual instrument height, and that would give us the slope, the vertical angle, and from that we could work out the distance and the difference in height. Typically with Stadia we can get accuracy of plus or minus 0.2 of a meter, both vertical and horizontal. But in their day they were used quite extensively for topographical type surveys. Could get reasonably accurate with those, and I used them quite a lot in mining for working out volumes and what have you. Well, I think we got reasonable accuracy with them, but it's now used in conjunction with a theodolite, whereas these days they would seldom be used at all. Cadastral title survey, possibly never. Building set out and control, never these days, and it probably never were in the past either. The steel tape and the long steel band. The steel tape is the steel version of the fiberglass tape, is essentially what I'm talking about here. They can get a slightly better accuracy of plus or minus 5 mils with a range typically up to 100 meters. You can use them, and that's for a single measurement. You can use them in bays or multiple measurements, but generally they wouldn't be used for a topographical survey, the steel tape. Possibly, with the accuracy, possibly they could be used in some specific circumstances for a cadastral title survey. Say, for instance, I know in the old days when we used to set up on the centre points of curves, particularly at cul-de-sac heads, you might use a tape. If you're just taping out the same distance, you'd want to be taping it out on the horizontal rather than using a slope and over relatively short distances. The reason that you'd use it is for speed and efficiency. However, these days with your data recorders and onboard EDM and stuff like that recording, it's debatable whether there'd be any efficiency gains in using a steel tape, or for that matter a long steel band. Building set out, they do have their uses in building set out. They can be very useful on sort of a horizontal concrete slab and situations like that, where you want to get tight measurements. They can be good for checking your EDM and what have you, and their accuracy, a little bit more accuracy there, especially if they were to be calibrated, because they have that steel core inside the tape. They're not as prone to stretching as the fiberglass tape. Control survey, seldom used there. Although we must remember that there's the small steel tape, which is the one we're all familiar with, that we hang on our belts up to about 10 meters. These, of course, can be used in all types of survey for measuring instrument heights and little short distances in and around the theodolite or where we are, or building dimensions or dimensions of street furniture and what have you. The long steel band, again plus or minus 5 mils, has a range of 200 meters generally, although you can do multiple, so you can probably get reasonable accuracy, probably up to about 1 kilometre, but that would be 5 times 5, sort of 25 mils possibly. It's plus or minus 5 mils per measurement. They topographical surveying, possibly in the past they were used for the measurement of control, for the topographical survey, in particular position control. Definitely in cadastral title surveying, anything before 1970 is generally done probably with a long steel band, and then the EDM started to coming into their own in the early 70s, and as we know by now, there's seldom the long steel band is used these days, evidenced by the fact that most of our trainee surveyors haven't used one and haven't seen one used in action that often. So for cadastral title surveys, pre-1970, this is what was used, and this is partly why we're probably telling you a little bit about these, so that you can get an appreciation of some of the data that you might be using as to how it was obtained and what was involved. They can still be, as I said, used in building set out. They do have some efficiency and some direct reading capability that can be useful in building set out, particularly on large concrete slabs and things like that. For control survey, I put in there seldom. However, if we read through the history of control surveys in New Zealand, we can realise that a lot of them started off from very accurately measured baselines, which were measured using long steel bands, but these were invar bands and measured in very precise situations, some of them taking weeks to actually measure these very accurate baselines, which were then formed the basis of triangulation surveys. The reflectorless EDM is the next one here, and as I have a Trimble S6, the stated accuracy of that is plus or minus 2 millimeters plus 2 parts per million. The reflectorless EDM, I've put that in here as slightly less accurate than the EDM. It's just a bit of a gut feeling, although the manufacturer doesn't say that. There can be a few issues with that you have identified the correct target, and they are range restricted, some of them, although those ranges are now increasing. So generally the manufacturer will have the range will be restricted. I know in the one I have, I think it's restricted to about 300 meters, but there are extended range reflectorless EDMs now which are measuring up to and over a kilometre. These can be used for topographical surveying, remembering that with most EDMs there can be a coarse and a fine range. So the coarse range would tend to be used for topographical survey because the accuracy and rigour is not required. However, under certain circumstances, there's nothing to stop you using the fine or more accurate range or measuring methodology that's there and available. So I think that's with reflectorless, it's the fine and coarse, and with the Trimble is tracking as a coarse range, and measurement or topo measurement is the finer range. So cadastral title surveys, the reflectorless generally is not used for the measurement of vectors. Generally used, I've only used it for topo shots to buildings, etc. But there are some situations where points are inaccessible that may need to be measured, that may form part of irregular boundaries and such like that, that the reflectorless does have a use, but in general we tend to go to the next stage down, the EDM. Building set out, generally not. However, opportunities can arise where reflectorless is used, and one I can think of where I was setting out piles. We'd drilled a hole in the ground, and then the piles were the top of the pile was being positioned 6 meters out of the ground, and so what I did there was put a bolt with some tape around it that the reflectorless could measure to, and the contractor could then, I could sort of be off to one side, and the contractor could move the piles around. I would tell them when it was in position, and they could nail them up and pour concrete around them, and to get them right. In terms of control survey, reflectorless EDMs never used there. I haven't quite filled in the box there, but yeah, oh well, that's how things go. Well, we might be able to actually fix that up just while we're here. I'll just let's just see what I can do. Just have to bear with me a little minute there. Get the colour right, get the pen right, get the felt pen right, and let's see if we can write that in there. Here we go. Never. And while we're here, I'll just take the opportunity to get the soft rubber out, and I'll just oh, what happened there? Undo that. Let's see what we can do. I'll just put a cross through that. Just so that we know that. Oops, no, still not quite got it right. I need to choose my pen, and I'll just put across like that there. I couldn't rub it out because I was going through to the background. Okay, well that's sorted out a couple of little problems there as we're going along. Now EDM, the Trimble S6, plus or minus 2 millimeters, plus 2 parts per million, range up to 5 kilometers. As I've explained, there is a fine and a coarse mode. I just might add that in there at this point. Just a note to that effect: fine / coarse. So we would use the coarse mode for topographical survey. Pretty good, pretty efficient. I think at these days it is the most efficient, so I can't think of any of these others being more efficient in that circumstance. However, you may not have that gear, in which case some of these other things will achieve the accuracy that you require for that survey. In terms of cadastral title survey, the EDM generally the go-to gear. Also, you must bear in mind here that with cadastral survey, our measurements and vectors are more often than not included in a closed traverse, or are they between marks, known marks. And we try to avoid using hanging lines, and where we do use hanging lines, we generally chain and observe them twice or measure them twice to make sure that we're getting the accuracy that required. So it's the EDM's the go-to measurement gear here in terms of the cadastral title survey. Building set out, they can generally be used in optical conditions, but we do need to take extra care. Perhaps one of the main things that we need to do is, if we're doing a pretty important and accurate building set out, is that we might get a recent calibration done on our EDM gear before we start such a project, so that we've got certificates in place that show that our gear is measuring both accurately, it's calibrated, and it's measuring accurately. It's measuring the distances, and we'll explain calibration a little bit later on. Now for control survey, of course, as we can see, used for checks for gross error topo shots, the reflectorless never, and it's the go-to gear for linear measurement, generally in a control survey, depending on circumstances. But nowadays we must bear in mind the go with GPS. So a lot of our control surveys are being done with GPS, but especially the longer range ones, but over shorter distances, perhaps on building sites and things like that, the EDM is still the go-to for linear measurement. So there you are. There's quite a lot of information in that little table there. Let's hope you can take that all in. Rightio. So what we're going to do now is just have a little bit of a look at how we might use some of this gear that we've talked about, the fibre tape. I've also, with the fibre tape, I've sort of included in here the handheld steel tape, which less than 10 metres, the one that we all clip on the side of our belt, used to measure our instrument heights and other little bits and pieces. Just a little handy thing that we have there, and yeah, we try and thing. So the fiberglass tape generally takes 2. It's best to apply an even tension to it, and generally we don't sort of try and measure what the tension is, but you'll find on some tapes that it's stated as to what tension the tape should be at. Generally we measure on the horizontal, although that doesn't exclude measuring on the slope, but we would need like an Abney level, or perhaps a theodolite, or our total station, depending on circumstances, to measure a slope vertical angle, so that we could reduce the slope distance to the horizontal. Some of these fiberglass tapes very conveniently have 2 scales, a metric scale and an imperial scale, which enables us to check. If we read both scales and convert one to the other, we shall get the same answer, and that's a very good independent check. There are a number of other ways of using the fiberglass tape to do an independent check. One is to get the chainman or the person at the zero end of the tape to set the tape on sort of another value, usually 1 meter. So then you would measure the distance again and subtract 1 meter from it, just as an independent check using different numbers, different part of the tape and what have you. This would apply equally with your handheld steel tape and what have you. Although the handheld steel tape, and must be said, can be a one-man operation, although a little bit fiddly when you're out 10 metres and trying to stretch over a drain or something. The other one is to read back from the other end. So say for instance you had a distance of 17.27 metres that you'd measured, slope or horizontal or whatever. What you can do is at your end of the tape, or whoever is at the 17.27 end of the tape can pull the tape out to 20 and hold that on the mark, and then ask the person at the other end of the tape to take a reading to see where that's reading. So typically in this case it should be 2.73. So when you subtract 20 minus 2.73, which you can record this in your field book or on the back of your hand or wherever you do, hopefully in your field book, you can record this as an independent check that you've got 17.27. So these are very good little techniques for checking gross error and sort of things that are maybe close together and what have you. So that's your fiberglass tape. Now the long steel band, as I said, they're traditionally used. The long steel band consists of a band 210 metres of thin steel, marked off in 10 metre intervals from 0 to 200, and then from the 0 on what is known as the reader, it's marked off in 10 centimetre intervals or 20 centimetre intervals in some cases, but nonetheless the metre, even metres are marked, and then in between those are a series of marks of either 10 or 20 centimetres. So what happens is you're at your theodolite end there, and the chain, and you've got a sort of a chaining tripod at the over the other mark there, and your chainman will walk out to the from the theodolite to the point at the other end and stand there. Then the surveyor will pull out the chain through the reader until the chainman finds the nearest 10 metre mark. Now in the example that I've got there, the chainman's found the 120 mark on the chain, so it'll be 12 10 metre lengths through to the 0. So the next thing is that the instrument man pulls up the tape and sees approximately where it comes on the reader, noting the closest of the divisions, the 20 centimetre or 10 centimetre divisions, and then finding the closest one, he then attaches a ruler, which is or a met stick, which is 20 centimetres long, has the centimetres marked out in millimetres, and that is attached at the appropriate point. So in this case here, 6.4. So the chainman there has got 120, and then the met stick is attached at 6.4. The instrument man, or usually the surveyor, then pulls up the band and applies a tension to it. Usually 7 kgs was, in my experience, 7 kgs, and pulls that up. The reason for the tension is to get an even tension on it, so that the slope, so that the sag correction can be calculated accurately with that tension. And so the instrument man pulls up and reads off the link stick in this case the 73 mils, and then records a slope distance of 126.473. Now unfortunately there I have put reduced distance. I'll just see if I can remove that, because that should actually be the slope distance. So this is layer 3 here. I'll just put that there. That should take that out. So we'll just go with that one there, edit, cut, and what I'm going to write in there now is slope. Hopefully, when I get it right, slope So that is the slope distance, of course, in there, which is the 120 from the chainman, the 6.4 where we attach the met stick, the 0.73 off the met stick. We also, when we're doing these, take the temperature. So we measure the temperature, which enables us to determine how much the long steel band has expanded or contracted, and we can apply a correction for the temperature. The tension is measured, which we now know we can now calculate the sag using our theodolite or whatever have you at the other end, at the end here. We can measure the vertical angle, and that enables us to make a slope correction, and generally depending on what height above sea level we're working at, we can make a sea level correction or correction to the ellipsoid, as it is now known these days, but previously a sea level correction. So using the long steel band, we can get a quite accurate measurement of distance. Again, you know, there are some things here you would want to have a recent, if you were doing highly accurate work, you would want to have a fairly recent calibration of your band done to make sure that it was measuring to the required accuracy. And that brings us to EDM, electronic distance measuring. And we've talked about two types of EDM here, to a prism and reflectorless, which is essentially the same as to a prism but with no prism. And as we've explained earlier, slightly reduced range in some cases. Okay, so electronic distance measuring, we set up our EDM either standalone, or these days most of the EDM is certainly integrated with the theodolite. And when EDM first came out, was an attachment to existing theodolites as that was needed, but today we have the total station where the EDM and theodolite are integrated and able to measure, well, actually reduce the horizontal distance straight out of the machine, but it does and is able to show you, you know, the slope distance. So here's generally what we do, and we record the instrument type so that we know what corrections to apply and what the instrument is and what the accuracy is. We need to know the prism type. There's some corrections and adjustments that apply through there. We measure the slope distance and the vertical angle. We still need to measure the temperature and the pressure, although these days the pressure is can be measured by some of the machines itself. And that electronic distance measurement, we're able to reduce that to the horizontal distance and effectively later on to sea level. So that pretty much ties up linear distance measurement and the tools that we have available. We will go into more detail on some aspects of that in further videos, and look forward to seeing you there. Cheers, goodbye.